So yeah, so we work with all sorts of people from all sorts of disciplines. Now, my background is mathematics, but it's always been applied to, or generally always applied to, glaciology. So the study of cold places. And the reason why I still like my climbing, I used to do a bit more climbing, going off to the Alps and things. And that basically got me interested in that. And it's for a lot of people, doing a doctorate as an opportunity to extend their hobbies. Although it took me a long time to finally get to Antarctica, and it was by this project. So yes, we study glaciology, and in particular, and it will make sense in a bit, the study of surface processes. So the stuff that you see when you see a glacier. Most science has gone obviously for the hard things or the harder things. So studying like the flow of ice and so forth, and subglacial processes. I enjoy studying the obvious things you can see, because often things get missed, certainly by scientists. Anyway, Lost Meteorites of Antarctica, great project. The idea kind of started like 2016, ended brutally, or not brutally, ended 2020 with a lot of, we was gonna have a lot of fanfare, but then obviously the world went slightly mad. And so it kind of got lost, and it got lost for me personally as well, because I then suddenly immediately flew into looking after the land, and everything just kind of was put on pause. And it was funny going back into my office 2 years ago, and so I took a couple of years leave to get the land going. And it was like a time capsule, my office. Nothing had been touched from the project. It was just full of bits of meteorites, bits of all sorts of equipment, maps and everything. And it was just, yeah, it was quite fun going back in. Anyway, so what on earth? So I know you know the answers to these. So first of all, if you want to ask anything technical about planetary things, you will know more than me, but I can prattle through. But what is a meteorite? Okay, so basically it's something which lands on Earth. The key from space, the key thing is that you can pick it up. So a shooting star is not a meteorite. It becomes a meteorite when you can pick it up. Okay, so that's the key difference. But it can come from all manner of places and things. It can come from, we get lunar meteorites where something's impacted the moon, the material's being ejected out, and it's come to Earth. It can be stuff that never really formed a planetary body, stayed out in the far reaches of the solar system. So there you can get meteorites which are older than the solar system, because they never went through the planetary formation process. So you get some really interesting information there. And also everything in between. So bits of asteroids and so forth, which have made its way to Earth. And that is, as you will be fully aware, is a whole subject in its own right. And it's a super interesting subject. I came to this from not the opposite side, but from looking at it more as I didn't come to it from that end. And that was a useful thing for the project we're looking for here. It came in from a completely different direction. People like Katie and Katie Joy and other people on there, their study is looking at meteorite samples. I do have a meteorite here that you can hold. I did have a meteorite here. There it is. So you're welcome to pass around. That's an iron meteorite. So that landed, I think, somewhere in Argentina, like let's call it the 1600s. It's that kind of time. It was found 1600s time. But it's an iron meteorite, and we use that for public outreach. And hopefully you'll notice how heavy the damn thing is. And it's dark. And it's dark because as it's come in, it's formed a fireball, it's burnt. It's basically like burning your blackjacks or your cake or something, and you get a nice crispy crust on the outside, and that crispy crust gives it's like doing anything. What's going on here? Oh, there you go. I can go back to perfect. And that crispy crust is a useful thing. It's called a fusion crust, not a crispy crust. But so this is an original photo KTF from ages ago, but this is a meteorite here, and as you can see with Antarctica, it stands out relatively clearly. Now, the first thing to say, why Antarctica? And the answer is, well, part of the answer is given by this photo. If one lands in Didsbury now, you're not going to know. If you go home and find, maybe a meteorite has landed in your garden, you're almost certainly not going to know. Because it will just be another rock in your garden. It doesn't form a massive great impact crater. It's just something that goes, and there it is. And they land a lot. That's the other thing. So part of this project, I think at the end, we came up with some, it's about 17,600, I think is our estimate, of meteorites or falls over 50 grams landing on Earth happen every year. So they're common as muck, and they're just really hard to find. Yep.
It's coming in quite fast, isn't it? How come it's sitting on the surface and not gone whoop,
I don't actually know what size this is. I'm guessing it's like that kind of size.
It's
No. It's just they don't come in that fast. They've lost all their speed. They're just falling because they come in really, really fast, Like, yeah, exactly, they're coming like 18 kilometers a second. And that speed just goes and goes and just comes to like normal free fall, like as if we were jumping out of a plane. So they come in fast, but for these sort of sizes, they've lost all their energy by the end. It's just dumph. So it would be like a rock being dropped off a tall building. You know, you get that sort of impact. But on ice, you've got to bear in mind, ice is a viscid fluid. Yeah, this is all solid glacial ice. And also this meteorite has probably come out of here. It's probably been around for a few thousand years as well, the Antarctic stuff. So everything, so if it did make a crater or land in, it's come out again, the ice has had a chance to swirl about. But yeah, probably make a little bit of a thump, but nothing too dramatic.
You did say you wouldn't know it was in your garden, but you would quickly be made aware it was there, wouldn't you, by the meteor sightings reporters?
Yeah, they don't see all of them though. They see a few on the fireball cam works, but they don't pick up everything. Oh yeah, and so if someone reports, yeah. So you meant to, if you find one, report it. Was it?
When you see one in the sky,
yeah,
you're supposed to report where you've seen it.
Yeah.
And then presumably with all the triangulation and everything.
Ish. It doesn't work that well. So in trying to find when it falls, you get a decent idea. It's much less accurate than you might think. And even the flow, well, you got the path initially, you can pick out roughly where it's coming from, the speed and where it's going to. It gets complicated towards the end because as it slows down, you've got the rest of the atmosphere blowing it a bit. So, you know, you might be within 1% of where it's going to be, but 1% from high atmosphere to down here is quite a big area it's going to be under. So you can find some, but they're called, we'll come to that in a second actually, but that's called a fall, when you see it and it falls down and you find the meteorite, but most of them are found. So you can see them, but I say most are actually missed in camera networks, because you've got some in Manchester, and they're great, but obviously when there's a cloud there, you don't see it. But yeah, we'll come to these the data things on it in a second. Well, here you go, something. So this is from data that was real as of 2019. Numbers have gone up. So what have we got here? Ignore most things here. So why iron meteorites? These are all places in Antarctica down to here. Until Antarctica here is the whole of Antarctica. These are specific places in Antarctica. Rest of the world falls and rest of the world finds. So a fall is when you see it coming in and you find it. So as of, call it 2019, 1,037. So a really small number compared to how many have come in. Rest of the world finds 15,000. So that's when you just stumble across one, or historically you found some. And the key stat here, and why I got interested in this, was this slight anomaly of these bottom three numbers. So crudely, we split meteorites into iron-rich and stony. So the Earth is a rock. Well, it's actually an iron core with rock on top. Everything else, the biosphere is just a detail. We're all obviously just details. The atmosphere is a detail. So we're just a rock floating on iron. If the planet gets smashed up, which the planetesimals, so the smaller planetary bodies which were there in the start of the solar system, hit each other, have collapsed and whatnot, their material gets ejected out, or it gets splintered out, I should say. And you can find bits of iron, which is the old core. So this would have been an old core or some sort of planetesimal, or the rock from on top. And you get the ions when the planetary body gets big enough that the iron, under the weight of gravity, can form its own gravity, that the iron can get drawn to the center. You form the center of essentially a planet, and the rock, the lighter material, floats on top. This is a process called differentiation. For smaller bodies, that isn't such a strong process. So you don't get such strong mixing. But that's partly what makes iron meteorites interesting. It's the core of X planets. But there's, you could put whatever definition you want on what's a planet, what's a planetesimal, but essentially it's gone through that process there. Now what we have here is this key number here, basically 5.7, same as 7.4. So order of magnitude is that you got 0.66 iron meteorites, so call it 0.7% of meteorites found in Antarctica, which is a big number, 40,000 odd. 0.7% are iron rich, okay? On the rest of the world, you're looking at, let's call it 6% there. So basically an order of magnitude difference. So the meteorite it collects in Antarctica, you got, according to this, 0.7% chance of it being iron. On the rest of the world, it's like a 6% chance of it being iron. So you've got this huge disparity in data. And these aren't small, none of these are small numbers. Okay, this isn't just dealing with like 3 meteorites, one of them turned out to be iron. There are thousands and thousands in here. So this is a statistically significant result of what's happened here. So the question is, where are the iron meteorites? Okay, and this is still in the same proportion. So many more meteorites being collected since the ones we are collecting now with these statistics. This same disparity exists. It still persists. The question is where it is. And where did this theory come from? So they're underrepresented in Antarctic collection. So it's quite fun for me because I enjoy doing icy things. So it seems like ice might be at play here. And you only find them in small bits. So if we were to go try and looking for the lost meteorites of iron, we're assuming it's not overrepresented on the rest of the world. We're assuming it's underrepresented as in they are lost. How the hell do you find them? There's been no UK collection mission out there. Where are they going to be? You've got a whole continent to play with. Where do you expect to find these lost meteorites? And how? So where are they? How on earth are you going to find them? And we have one attempt to find these. Okay. So that was kind of these big issues. So put these into your mind. So suddenly you had something that where are you going to find these? And you got one shot at finding these lost meteorites. Here we go. So anyway, so this is kind of where I come into the problem. So the key of maths is not, the sort of maths I do is not precision. I detest precision. I love approximation. And it's far more powerful because you get lots of crude, it's order of magnitude information. That's what really, and you do your astronomy. Like, if it's 9 light years or 20 light years, it's still, it's not 1,000 light years. It's the same number. When you look far enough away, these things become the same. And it's a bit like this modeling here. So what I have here is a nice icy block of ice with the sun above and a meteorite inside. My academic background is generally studying these sort of processes up here. And you get some really fun processes with rock and ice interaction. And that's what I enjoy studying. And get some lovely things on Earth with the interaction between rock and ice. And we were playing around with this, and we actually predicted there would be a different disparity here with meteorites before even chatted to Katie about this. So we had a kind of a daft idea that there might be some meteorites hiding under the ice. And we had that idea before we knew they were hiding or potentially hiding under the ice. And the idea was this. So if there's meteorite, let's suppose it starts off near the surface. So this could be a centimeter, it could be a millimeter, it could be a meter, whatever. It's a distance below, but something where it's near enough to the ice. And this ice here, we can suppose is clear. So it's not got a snow layer, it's quite clear ice. And what I want to do is to somehow model the behavior of this meteorite. So it's stuck in ice, you think it's going to go nowhere, okay? The sun's coming in, some ice, or quite a lot of ice, you can actually shine light into it. So this represents ice attenuating to hit this meteorite. If you get enough sun touching the meteorite, potentially, the idea is that we can start to melt at the bottom or at the top, somewhere around the surface over here, to melt enough of the ice, because this is a dark material, so it's a higher albedo, it absorbs more solar energy than the ice. So the photons are basically bouncing around through the ice. With here, they get absorbed more readily on the rock and the dark material here. You might be able to, over time, absorb enough energy that you can melt your surrounding ice, start to form a bit of a melt pool above, and as so doing, you can then start to melt downwards. If you get hot enough, you can then melt this thing down. It basically melts downwards, and this ice in the blue ice area, in the ice areas of Antarctica, is actually flowing upwards. Okay, and we'll come to that in a bit more in a second. But in Antarctica, where you find meteorites, they're in places called the meteorite stranding zones, where ice has got predominantly an upwards direction. So it's being brought up, and the meteorite we have this idea, as it gets nearer and nearer the surface, it can melt its way back down. So we get these opposing processes. Just a theory when we started off. Literally, it was just a bit of fun glaciology, just messing about. No idea if this is physically possible. No idea if this is going to explain the collection shortfall and why that might explain it. But it was a fun idea to mess around with. And that's what we started off doing. Now, see, the maths of that, before we could even do some physical experiments or anything, basically just some maths. And as I said, with approximation, you could turn this diagram here, ice, water, stone, ice, into something like this, a 1D model. So for those of you interested in trying to solve hard problems, just get rid of just try and make things simple. And again, you can turn it into something called basically a one-dimensional problem where that's the only dimension. You say it's infinitely long in either direction. Because you still have the same physical interactions. You've got physics going on here at the surface, conduction here, You've got melting at the bottom where you then put the water up here. That layer depends on how much is melting here, how much is refreezing or melting up here. It's the same processes. So you get that same, roughly the same balance in the size of your physics. And crucially, it makes the modeling of it so much easier. So if you want to model that, you want it for years, okay? And it's pretty boring. You're doing it for years, okay? You've got to buy a computer package. You're probably going to miss most of the key physics. And you're just messing around to gain 1% more information than you would from there. Okay, it's absolutely pointless. So here you get a lot, and here we can actually draw out and understand the physics and look at the balances. And the other ones, it'll be a pretty picture, but you can't, it's really hard to draw out what is going on. And the reason why is this. Now, if you don't like maths, don't worry about it. The punchline is that diagram before, you can break down to this model here. You're not expecting anyone to understand this, but the point is, and you just take it from me, these are actually really straightforward. Once you've been given these are straightforward to solve. What I mean by that is you could take it away and put it onto an Excel spreadsheet and just press go a few times. This gives a time evolution. It's straightforward between here. And that's a lovely result of this. And that's what makes maths, or the sort of maths I enjoy doing and promoting, is when it becomes useful to other people. It's all fair enough, doing stuff on a computer model. No one can replicate it, okay? And so you get dodgy results, and it's just slightly pointless a lot of the time. But here you can independently do this, and it means you can do lots of other things with it. So once we got that, so that was some really fun bits. There was actually a lot that behind the scenes that went on there, but it's a lovely result. We could then apply it to the lab. So this is suddenly, it was like, oh, right, we're doing experiments. I'm not a natural experimentalist or physical experimentalist. But what we've got here, and this was it was an MSc student at the time, a guy called Mike Coughlin. We've got three photos here of an iron meteorite in ice. So it's basically a lump of ice here. This is the depth here. So this is the surface up here, the bottom down here. We have a solar simulator lamp on top, so a light bulb which has the same spectrum as the sun being shone on top. And what we did, we applied it to this. And bear in mind, we did not know if this was physically possible. So we came up with the maths of it, and goodness knows if it's going to work. We could stick it on top, and it took a load of fun. We started off with just using a desk lamp, which didn't work because you don't have enough infrared coming out of it. So we played around all of this, and we then had to make it not melt on the top. Because in Antarctica, there's no melt on the top. So what we wanted is, can we just get this thing to melt itself? Can it go down? Can it absorb enough solar radiation that it can melt? And we got that working. We got this process here. And so you can see this is however long, 80 minutes later, 160 minutes later, this thing moves downwards. All in lab conditions, not Antarctic conditions. So we have different temperatures and all sorts of things there. But straight away, that is a great result we got out of this. That was physically, it's possible. And so suddenly it's kind of, right, it's game on now for explaining this meteorite, these lost meteorites. We don't know quite why yet, but this first thing we could show that. And do I get it here? Yes, I do. So we can then, what was the nice thing there? We could then do the maths, that model I showed before, to the laboratory conditions. And I can get the maths, in the lab conditions, we could be very precise with the inputs into the maths and go, well, let's put this into the model. Does it replicate what we see in the lab experiments? And the answer was it did. When we had that, we could then go, we'll change the parameter values. So what I mean here is these numbers on the right-hand side of the equations. We can make laboratory versions of these numbers here, put it in and get numbers out. If it then matches with the physical reality, we know we've probably got most of the key physics in there. So it's good. It might be a fluke, seems unlikely, but we won't have all the physics, but we've probably got the main thrust of it. We could then change those parameter values to an Antarctic setting, of what we can, it's best we guess, for an Antarctic setting. And we could apply a time variation on it. And this was the lovely punchline of this. So if you just look at, say, the left-hand one of these two graphs here. So on the bottom axis, we've got time in years. On the top here, we've got depth, ice depth. So here's 0, and then ice is going down. These ice sheets, hundreds to kilometers deep. Okay, so we're only interested in the top few tens of centimeters. And as time goes on, like I say, the ice predominantly is coming upwards. Okay, these are in the areas where we collect meteorites. They're coming upwards. And as they come up, you get this kind of sawtooth motion starting to appear, certainly for the ions, because as it's getting up and up and up, you can feel more sunlight, which is coming through the ice. As it gets that, it's got more chance to melt back down. And this is the annual cycle, because obviously in the summer months down there, it's a lot of sunshine and then nothing during winter. So it rises during winter because the ice is still coming up during winter, and then sinks back down in the summer. So that's summer, winter, summer, winter. And lo and behold, we get this cracking result out here, where for iron, we get it hanging over here. For an ordinary chondrite, as in rock, it comes up. The difference between them isn't actually the albedo, or we originally thought it might be. Maybe iron's darker than rock. It doesn't actually hold true that, because these things, like I say, it's a burnt biscuit. So that was all dark brown. What the difference is the thermal conductivity. So it transmits its thermal energy much more quickly. So it's a bit like a frying pan. It's trying to cook on a really good frying pan, straight away, you stick it on the cooker and it's straight through. Put a bit of stone or a bit of wood on there, it's just not going to conduct. You'll be there for hours waiting for the temperature to come through, okay? But so iron transmits really quickly. So the sun comes down, hits the top of the meteorite in the ice, and it can quickly transmit it to the bottom before it's dissipated or stored inside, transmit it to the bottom to melt the ice, and then it can go its way down. So that was able to draw out, that modeling draw out what is the key differentiator between iron and rock and stony meteorites, and it crucially showed it was physically possible. So suddenly everything is up there for explaining the lost meteorites. Go for it.
So are you saying that in the left-hand graph that the meteorites are generally going to be about 0.4 meters underneath the surface?
In this 1D model, yeah. We updated it later, but it's that sort of size, yeah.
And it goes up and down.
Yeah. Yeah.
And it gets hotter and then goes back down again.
That's exactly it, yeah.
So I'm just confused. You've said that the meteorites, the iron ones particularly, tend to sink because they're melting water, which is tend to sink, and yet on that they're going towards the surface.
So the ice is moving it up. So the ice flows. Now it's just coming up. So basically, you've got a mountain range here.
Yeah.
The ice is trying to make its way out towards the Southern Ocean. It hits the mountains, and the ice does this motion here. And so that's in these particular regions. That's what these meteorites come upwards. So they're naturally going towards the surface. But then, yeah, then it gets too hot for the iron ones and goes back down again.
So if you had a chunk of ice and not the rock, you're just looking at a chunk of ice, it would come up.
It would come up to the surface.
Of the
Yeah.
chondrites, and that's more than the iron.
Yeah. So this is all just ice basically flowing upwards. So if you put like a tennis ball in there, it would just. But it's like you're talking, 3-4 centimeters a year. It's moving upwards very slowly.
You've seen that.
So why have they sunk in the first place? You said earlier on that they don't run with any impact as such. So how come they've gone below the ice surface?
Because thousands of years before they landed several kilometers that way.
Oh, I see.
And it's then that gets covered in snow and so everything is very, very slow process. It gets covered in snow and then gets subsumed into the ice. And then in these particular areas where the flow comes up, so these are, we'll see in a second, the meteorite stranding zones are basically eddies in rivers. So those of you like your, I don't know, your fly fishing or something, you get slower portions in rivers where food collects behind, so bits of morsels or bugs and things, and the trout will go for it. Okay, so they come along to the river and you get these little eddies and slow bits. And that's a good place to go. It's a bit like that here. So the ice is flowing along, it hits somewhere like the Transantarctic Mountains, and you get parts of the ice which suddenly slows down. It's slowed down, it then needs to then kind of basically, as conservation of mass means it's then got to flow upwards. So you get these strange areas which flows upwards. It's so high, and because it's flowing upwards, the wind has so long to blow, it blows off all the snow on top. So originally it gets snow covered, in these areas here, there's no or very little snow, and it's going that way.
We've seen that same thing with airplane crashes in Argentina.
Okay.
Glaciers.
When it goes
17 or something,
Yeah.
crashed, covered with snow, sank because
Yeah.
it was obviously hot. And then as the glaciers descended back towards the sea, it's popped out.
Yeah, exactly. So
Back to-
you find it with human bodies and things and all
Yeah.
sorts. It's yeah, there's all sorts of interesting things that pop out of glaciers. But yeah,
So the ice is blowing up.
yes,
Is the
and a bit
surface-
sideways, but yeah.
You're talking about an upward moving ice.
Yeah.
Is the surface being lost to melting?
There's exactly, it's going through a process of either sublimation, so going straight from solid to gas, or probably a lot, equal amounts we estimate, it's actually just scouring. Just the winds are so strong, it's sort of spin drift, it's just scouring away. But a lot is from sublimation. You can get bits of melting, it's very rare, because obviously the temperatures are so low. But generally sublimation going out, but it's a really slow process. But in terms of but because these things are in equilibrium, they've reached a height where, or the ice surface reached a height where the upwards flow equates with the mass loss on top. And if it wasn't, you wouldn't get many meteorites there because there's not that many meteorites in the first place. And these are, so to go into a bit more detail of these, so Antarctica, so these are UK, this is the UK, British Antarctic Territory over here. So we claim we own that, other people claim they own other bits. And we all agree, or we all agree that no one's going to do anything about it. We're going to not stop our claim on that, but we're not going to do anything about it. And it's a really useful, so if anyone's interested in a bit of like how countries can actually be collaborative, the Antarctic Treaty is a really useful one, where everyone goes, well, it's still mine, but I don't care as long as you don't start caring. And so everyone agrees no one's going to care. And so it's a useful way of doing things. But the way you retain your claim is that you do science. So crudely, this is why there's a lot of Antarctic research. It's not because it's really interesting. It is interesting, but that's not why you fund it in your taxes. You're funding it for international relations. And it came about during the Cold War when Russia, America really didn't want this heating up. And so they had this lovely agreement. So that's why there's a big bias to here, where perversely, I mean, how many documentaries do you look at about the Arctic? It's all about the Antarctic. The Antarctic is up the road. You know, we're whatever, we'll be up 50-something degrees here. Yeah. How many times do you go up to the Arctic? Probably hardly ever. It's just there. So it's interesting, but down here, people are there the whole time. We've got all these bases and stuff. Anyway, so this is the main UK base. Rotherham, Halle, the really fancy looking one. And these across here, this is the Transantarctic Mountains. These blue dots are where the blue ice areas. Sorry, this is blue ice. So that's where ice is exposed. There's no snow on top, and it looks very blue. So when you see it on the map, it looks blue. Okay, so blue ice is glacial ice. The rest is covered in bits of snow. These squares, which hopefully you can see around the place, the black squares, I should say, with a white insert, are where meteorites have been collected. So you might know some vaguely, you've got Allen Hills, which you might have heard of in regards to meteorites. They're kind of within the world of meteorites, these are all quite well-known areas. Generally by the US, NASA go out every year collecting meteorites, predominantly to this southern end. So, because they have research bases down here. But yeah, you can see there's a huge preference to finding these in this region, and they correlate very closely with the blue ice areas. Okay, so that's basically, and on the coast, you do get some, but it's a lot of that might be more just the winds blowing the snow off rather than being a good place to find meteorites. So yeah, so this kind of limits, well, just kind of highlights where it's got theory of how meteorites or iron meteorites might be lost or might be hiding. And then the question is, how on earth are you going to find them? I got what the next slide is. So yeah, it's basically, here you go. Here's an explanation of all of this. So we've got ice flowing this way, so from top to bottom. Snow's landing on the continent. Okay, so and we're talking over thousands of years. You get a lot of it, obviously, but over those timescales, it's a lot. And we've got this mountain or nunatak, or kind of a nunatak underneath the ice. Is rocky lump over here. It slows the flow of the ice, basically deflects it upwards. As it goes upwards, the wind has more time, because you lost the horizontal component. The wind has more time to act onto the surface, blow away the snow, and it leaves this lovely blue area. And so a meteorite landing upstream can get covered by snow, go into this, and they can come up onto the blue ice surface. There's also direct infall as well. The size of these blue ice areas, you're talking the orders of kilometers to tens of kilometers of area, 10 square kilometers to tens of square kilometers of area. So they're big areas, but they're not a ridiculous size. So, you know, something the size of probably Didsbury in its total would be one such field. And yeah, this is the main mechanism. So it's this final process, these arrows coming up, that we were then looking at. And in particular, you can go in and have a look at these. So here are 1, 2, 3, 4, 5 well-searched areas by various, so Allen Hills in the bottom left here. NASA searching over here. La Paz has been NASA, I think. Saul Rondane, I think that's the Belgians, I think. But there's 5 areas there. You can see in detail there and where the meteorites are located in them. So the red dots on these bluish outlines are where they found meteorites. And what we wanted to do from this is that we needed to work out where within that British Antarctic territory we would go to. Okay, so we've managed to get funding. So after we'd done that idea, we published a paper. It got vaguely well received. Was then able to get funding from someone called the Leverhulme Trust, who fund, say, adventurous science. And it was really good fun putting that together because it was such a adventurous project. It was a ridiculous one. And they really enjoyed it. But we then, as part of it, there's a first to get them involved. They don't give that much money, relatively, but the project was going to be in total probably millions because the logistics involved. But the British Antarctic Survey supports research councils. So if a research council says, yes, we wanted that project, the British Antarctic Survey then has to do all the logistics. But they never worked with the Leverhulme Trust before because the Leverhulme Trust is a private charity. And they wanted to use a test case to see if BAS would do this. And BAS wanted to use it as a test case if legally they could. So we had to get the approval from the head of the Leverhulme Trust, the head of the British Antarctic Survey, and some Foreign Office people who fund the British Antarctic Survey to agree that if this got funded, they would support it. So it was quite fun doing actually the mini politics of this before it was even got done. We had that idea, then we had to do the politics, get that, if it did get funded, it would happen. In hindsight, that probably really helped matters because you got the attention of the powers that be. And then they did fund it. And it was wonderful. Then suddenly it goes from this, that bit of maths to a bit of laboratory to this question of where the hell do you go on this continent? And it's literally, you've got 3 years to go and you've got to find some meteorites. And you're going to go somewhere where no humans been before because we couldn't go to somewhere that people already searched because they've already taken the meteorites. And we needed to look at the full collection data to look so pure. So that's a tough ask. So going somewhere, there's plenty of these areas that people go to and there are no meteorites found. Okay, it's probably the majority of the case. You go somewhere, you might find 1 or 2, but you're not going to get any proper data out of that. And so it was a really tough ask, and that was great fun. It's something I just wallowed in because it was like you've got this huge area over here to find somewhere to go. And that's, again, we deployed a lot of maths again to work out where we're going to find meteorites, where on that continent is most likely, or within British Antarctic area, or somewhere that the British Antarctic Survey can support, are you most likely to find meteorites. So you have all these constraints of whatever time, vague, lat longs, and place. We didn't want to go anywhere near. There's lots of rock on the surface as well. So some of those meteorite stranding zones, you do have mountains poking out of the ice and rock flows off. And so it's actually hard to find a meteorite because maybe 1% of meteorites because the rest is just rock. And that's fine if you've got lots of time. 1% is pretty good compared to, say, here in Didsbury. But we didn't have that benefit of time on that. So where do you get most meteorites out there? It's a really good problem. So a lot of modeling went into that first diagram with that ice flow or the previous slide when trying to work out how many meteorites, if they were landing on a bit of I'll come back with it. If you had a certain known flux landing upstream here in this catchment area, if you knew how many meteorites per year were coming in, and you knew the rest of the physics here, you can estimate how many meteorites you expect to find on the surface at any given time. Okay. Fortunately, we have a map. We all have a map of all the blue ice areas in Antarctica. So we were able to basically get that map and then back out, then start doing, you get that map and then you go, well, these are areas we physically can't land near. These are the areas within British Antarctic territory. And you start to get down to, say, maybe 20 blue ice areas that you could possibly go to. And then you want to do, well, if it's all constant flux coming in, which ones are going to have the most meteorites? And they've all got different flow velocities, different ablation rates, because it's a bit like the weather here compared to, say, 10 kilometers, 1,000 kilometers down the road, very, very different. And it's the same here in Antarctica, different processes going, different weather patterns going on. So basically having to create a rank order of where it's going to have most meteorites. None of us have ever been there to know if they actually hold meteorites, so it's all a bit of faith. And then you've got the other question is, well, how many meteorites are actually coming to Earth? Okay, and it's a lovely open question. So those of you read into your data, and you probably have looked at this, so the Centre of Near Earth Observation, I think it's basically a NASA-run database of large fireballs over Earth. So it's set up for late 80s, early 90s to monitor, basically set up to monitor nuclear missiles coming in. And it's a really useful thing. So it gives you the velocities coming in, the lat longs and everything on there. But it's a good database to look at. There's lots of holes in the data, and it's only really got more accurate until perhaps the late 90s, early 2000s. And they don't basically reply to your emails when you ask for more things there, because it's sponsored by the Defense Department. But then the Defense Department releases data to NASA to say, here's some fireballs. And what I have here, so this was true as of, call it 2018, over here. And it looks to me, so this is the equator, this is the North and South Pole. So we put the data together, North and South. And if you eyeball that, and you didn't say that 63 was there looks like quite a clear decline in these things. There's a preference to the equator. Okay, and that seems to make sense when you think about it, and it's always dangerous to think about it, but when you do, you can see there's a preference to the equator, because most material, as you guys would know, is coming from the asteroid belt, within the plane, because everything, yeah, it might be here, it might be there, but it's all the same between friends, isn't it? So this material is coming in, it's basically all going to the sun and going around the sun and coming back. And if I'm facing into this material here, where my most likely to be hit, it's going to be my side facing into it. Nothing's going to hit the top of my head. Okay, because it's going to go straight over the top and go over there. So you can see one particularly, if you look at a sphere, you got more surface area facing into it. Actually, I have a better diagram here. Here we go. So this is obviously the Earth here, and let's suppose some materials coming in. That's the best way to think about it until you realize you shouldn't, well, you thought about it too obviously, or you shouldn't be thinking about it, because you got gravity suddenly kicks in. Okay, so it's not, is it the case? Is it the most surface area you're looking into? Or let's suppose I'm just my size, okay? Literally, I'm looking to the asteroid belt, nothing's going to hit me here. But let's suppose I've got the density, I'm sure people would argue it, the density of a black hole, okay? When suddenly anything coming this way, it's just going to be, there's be very few actually bang on my midriff. You think I'm only, what, 1.80 meters? Nothing's going to hit there, is it? Lots of things are going to be coming in from the top. So there's a huge preference, and also at the bottom, huge preference to over here, things coming in from above or below. And it's like that with the Earth. This material isn't just going in a nice flat plane. A lot of it will be going over the top of the Earth, and if you have enough gravity, it then gets bent towards the high latitudes or the low latitudes, depending on how it's coming in. And then suddenly you've got this balance. Is it your surface area, or is it gravity pulling it in? And which wins in that trade-off? So are you going to get more meteorites at the poles or more at the equators? It's a tough one. And it's one you can't answer until you actually put the parameter values in. And it's a lovely problem. It's a really, really nice problem. And hats off to the person who actually solved it. I think it was, I've got his name a bit, a guy called Halliday, and it must have been like the 60s. He never showed any maths, so he worked it out, but we got exactly the same result as him. And we did have to show a lot of maths. So it's, but yeah, and so if you then go through and do all the work on that, which is a great problem, and it's great because it's basically undergraduate physics sort of level problem. So it's a nice academic problem, but it's equally, it's not, you know, you're not splitting the atom sort of problem. And when you solve that curve, which is what this wavy line here is, and you scale it, it fits it really nicely. Yeah, it's not perfect. This 63 still being a pain over here, but it works really well. Okay, basically you get a nice flashes curve and it tails off over here. And the other thing is you compare it to what anyone else has done, and the nearest that someone else has got to trying to model it and was this flat line in the middle. Okay, or the flat line's uniform, the other one's that, and it's just, and then so you can do all sorts of stats on confidence levels. And yeah, so we're pretty happy there. But the punchline of that is that if you know your flux, say elsewhere on Earth, as in, you know, how many meters, supposing you do know for definite how many meteorites are landing on Didsbury per year. If you know that, you can then, so you've got that flux, the number of meteorites per year, you can then go down this curve, and you can see that if Didsbury's kind of over here, whatever latitude we are, well, probably 50 something here, you can then go along here and just look at that percentage drop to predict what they'll be at the North or the South Pole. Okay, so if you know something where you are, you can do that. And that was a great result. But then I went down a rabbit warren of really fun bits of science there, because it turns out lots of people look at this type of problem. And you can make good predictions on how many meteorites there are going to be. And from doing all of that mathematical modeling, and there was so from the math modeling, we were able to use the meteorite stranding zones where the Americans had been and other people, but we hadn't been. We could then work out from that glaciological modeling the flux of meteorites there. So we had those blue ice areas. We're then able to take independent meteorological wet data sets to work out what was sublimating, what the snowfall was, used mapping data to work out the areas, to work out an effective flux for Antarctica. So we've got that there. We knew their latitudes. We could then, so that gives us our estimate, and we could then go along that curve to compare to elsewhere. Now, these two characters, Halliday and Bland, were meteorite guys. Meteorites, and they, I think Halliday had a camera network over Canada. Bland, I'm going to get it wrong, but I'm going to say the Atacama Desert. It's somewhere like a dried, I think it might have been the Middle East actually, but I'm going to call it the Atacama. That's a good place to find meteorites. But basically it was somewhere much nearer the equator. And when you equate for that variation, you can see that their flux of falls, so 51 falls, so number of things over 50 grams per million kilometers squared, 33.1, and we get 38.7. Basically, we're pretty much in the middle of what these two independent ones had. So these are, and continually through this project, because we're so out there, it's just like we need to somehow link into independent data sets. Because we're probably doing new physically experimental stuff, mathematically experimental stuff. Everything was high risk. Anything we could get as an independent assessment was wonderful. And getting this result was fantastic. And that got its own story as well. So whilst everyone was locked up in home, I remember one time I was there with Jonathan Amos giving a talk on the World Service or the BBC, or it was radio at the time in 2020. And it was quite fun saying, this is really interesting. And everyone's like, oh, everyone's dying. But anyway, so I got lost somewhere in that talking about it. But that was, if anything, this was the main punchline from the, scientifically, probably the main punchline from the project. But that's not what I'm here to talk about. But it was an extremely useful validation of everything we're doing. And it enabled us to then, if we then know the flux in Antarctica, and we could do that with the Antarctic data, but equating it with these meant we could do it confidently, we could then work out where we want to go on the continent, okay, and come up with a rank order of where we want to go. We did that. We have an idea of where we want to go. What has that got to do with landmines? So this is the next bit of the project. So we have all these facets going at the math, the physical side, and landmines. The question is, how the hell are you going to find these things? We predicted they're, centimeters to 10 centimeters below the surface of the ice. Okay, not only is it hard enough physically to get there, hard enough to, when you get there, to have predicted there will be meteorites there, but then you've got to find something you basically can't see. But that sort of depth is pretty opaque to the human eye. You're not going to be able to see it. Or you've got to be standing over it to have a decent chance. So we then had to develop a whole load of detection technology to find these. Fortunately, turns out Mantra is a bit of a hotbed of landmine clearance. So there's all sorts of projects we've got on here. They've got a Nobel Prize from not the university, but in the centre of the town. When Princess Diana was doing her work, there's all sorts of charities in town that do stuff. But there's an engineering group in Manchester who also do landmine clearance, the University of Manchester, who do landmine clearance work and develop very fancy metal detectors. And being who I am, basically I was just kind of going around the university trying to find anyone who would happily get involved to receive basically no money on this and just to work a lot on this and develop some technology. And we did, there's a whole group of them, they're fantastic characters. There was a guy called Tony Payton around the group, but then Liam Marsh and John Wilson, a guy called Wouter, who all helped heavily in this. And it was the creation of this technology. So this is basically the end product. So this is down in Antarctica, but it's this thing in the middle where basically you've got this triangle at the front, you strap that to the back of your Skidoo, and on the very back, you've got these metal detecting panels. So you've got 5 metal detecting panels, each independent of one another. It might sound like, oh, it's just a metal detector. It is so hard, the science involved and the engineering involved, because you are smashing these things up. Metal detectors do not like being hit. Who's ever been metal detecting? And basically when you're going along, every time you move your hand, it goes, woo, woo, because every time you change direction, it kicks it off, okay? The things don't know, when next time you go from Manchester Airport, just whack the machine, just for fun and kicks. It's going to take about, just give it a little tap, it's going to take about 20 minutes to reset. It's so sensitive, that stuff. So for this, it was like, well, we are going to be obliterating this machinery in really cold temperatures. And we'll be bouncing up and down like mad. And this was a really, really, really hard bit of the product. It was the hardest bit of the product. And it was something completely out of my expertise. So had to farm it out to people and then work very closely with them in speccing it up. But that's what the end product is. And we did lots of testing on this. So the project, I say, was crammed into 3 years, literally going from getting the funding and it's like, oh, where do we go? What the hell do we do? To having to get everything up and running. So Svalbard up in the Arctic, very close, 2 low-cost flights away. If you've never been, has anyone ever been to Svalbard? It's wonderful, isn't it? Yeah, beautiful. You should all go. It's 2 low-cost flights. Wonderful place. Keeps the Russians out, keeps Norway strong. It's a great thing. So again, it's a bit of a political hotbed up there. And when you see it physically on the globe, when you look down from the top, you realize why strategically it's incredibly important. And over here, this is a NASA base actually. Over here, there's a huge US presence around. And anyway, so as part of that project, this project, to get it to work in Antarctica, we've got to damn well hope it's going to work okay. So to do that, we can't just keep on. We only had 2 winters we could possibly go to Antarctica. But the UK have got a research base, a tiny little one up here, and a place called Meteorites in Svalbard. It's magnificent. And so we were able to go up here. We did 2 projects on doing this, 2 seasons go up here in March time. It added so much fun for logistics because you're going up there in March, but then you've got to ship the equipment up there. So you've got to do it before the sea ice freezes. So you've got to post it in November to get it up there. Then you've got to get it back, and then you've got to get the shipping deadline for Antarctica, which is August time. And then to get that back, you're not getting it back in time to go to Svalbard again. So this postal service thing is just absolute chaos in the project. And remember one time I was dealing with postage to both Antarctica and the Arctic for things where I needed the results of one to the other. So it's like, how am I going to get this memory stick out of this thing and get it working here? And it was just absolute chaos. But this is us testing it up and down. So this is me driving a yellow suit up and down here. Just basically nice cold conditions, and we created an artificial runway with flags on. We buried decoy meteorites in the ground, based on iron objects, and we can go and test it. So this is us here, stood around. And again, part of the fun, it's such a wild project. On our backs, you can't quite see there, but we've got rifles on our backs because we then had to go, because it was just us, we had to go to polar bear protection. So it's kind of bizarre. So you're driving along with a meteorite collection thing with a rifle on your back. So it's a bit like Mad Max, the whole thing. And to make it worse, to actually get the meteorites out, I'd have a rifle over here, but also chainsawing. That's the way we can get. So part of it's all ready to be on all sorts of chainsawing things to then how we'd extract meteorite if we found it. You then in the middle of nowhere had to be chainsaw. We did all sorts of practice and how you would get an object out of the ground where you didn't want to strike it with the saw. It's an issue where you've got proper glacial ice, really hard to get into. How are you going to get something out of it? You might have found it. You're not going to do it with hand. You're not going to do it with a chisel. So anyways, that was, yeah, it was great fun, but it was and this is actually us in Antarctica. This is sky blue. So sky blue is at the end of the Antarctic Peninsula, as in the southern end. It's a UK landing strip, but used by all sorts. It's a blue ice zone. And this is one of the mountains behind. So that way is Rothera, that way is Pole. And this is us having a great time because we're just testing stuff out here. So these, you can see 5 panels on the back of the Skidoo. This is me taking the photograph of it. And yeah, just getting data and just creating these landing strips, putting decoy meteorites underneath, testing it at different speeds. So does it work at 5 kilometers an hour? Does it work at 30 kilometers an hour? Bear in mind, a Skidoo can go like 70 kilometers an hour. You don't want to be doing that fast, but trying to work out the optimum speed because area is everything. As an area you can search, because when work out the flux of meteorites, you then know how many meteorites you expect to find. Well, it should be in an area. You then know how many are missing because only about 5% are going to be iron. And so you're looking for 1 iron meteorite roughly per square kilometer. So imagine a kilometer there, and you are looking for an object typically that big, tens of centimeters below the ice. Okay, with a bit of equipment it's been designed for this. That, you know, the odds, everything on the project was high risk. And yeah, so that's what you're dealing with. And so hence why being absolutely parallel and doing as many testing missions as we can. This is all built and designed by the team. So really hard. So like I say, a kilometer, and you've got to find a stone like that. Horrid.
Are those solar cells on the?
Yeah, got solar cells. We've got batteries inside, solar panels on here, computer equipment in there as well. Computer equipment over here. Yeah, spare all sorts. Yeah, and the solar actually worked pretty well. That was pretty robust. And of course, to get that going, I should have had this first. Actually, as far as the 2 Svalbard, forget that. This is the way, and this is the biggest high risk thing. This photo, Boris Johnson was over here somewhere because this photo was taken the day after the Wadey Bridge dam burst. If you remember that, when it all came over. So this is one of our fields over the back. So the dam is down here. So this is the Cat and the Fiddle. You know the Cat and the Fiddle? That's there. That's Shining Tor over here. Wind Gathers over here. This is Ladder Hill up here. We're on Eccles Pike here. And this is how we started off messing around. It's a lovely wildflower meadow, but they had to get the meadow. By definition, a meadow is cut. Pasture is not cut. So it's in wildflower meadows. We got it, had to get it cut in time to do the experiments, then go in, make little holes and put iron objects in here. So even before doing icy conditions, you've got to see, does this thing even work? And with vibrations, does it even ping? So you then have to change this. And as you all know, with computing technology, or anyone with an electric car knows, when it's cold, the electric car is pretty crap, isn't it? Because everything changes at cold temperatures. And here, with a really hot conditions, so we just had the hottest day ever recorded in Whaley Bridge, which then caused the dam to burst. And then we're going up and down with a black panel in this heat. And so obviously it's extremely hot, this stuff is. So it's like the polar opposite of everything. But you're just trying to see, physically, does it work? And what does it take to break it? Also, is a key bit of it as well. But yeah, on the back of that duster, up and down you go. And then that was whatever years they were. That is 17, 18. And then this is the field piece in 18, 19. So this is the same time as me going to Sky Blue to test the equipment. We then had to send Katie Joy, the meteoricist, to some of the areas we wanted to visit to see, do they have meteorites? So we came up with a short list of places, and then we then said, well, these ones have the highest concentration of meteorites. We then had to send her to those that year before we take the equipment out to them to see, are there meteorites on the surface? So in its own right, that would be a huge, great thing. The logistics is massive. Everything's colossal about it. It was the first UK collection ever. And they were the first humans ever to these areas. So it would have been its own thing in its own right. But because it was so daft, the product that we had this equipment over here was purely like, you just go there, see it, and you come back and tell us about it. But it was quite fun when we were here, because I was in Sky, I'd done my work at Sky Blue, came back to Rotherham. By the time Katie was out here, she flew from Halle down. We were in radio communication, and it was quite fun. Suddenly it's like, yeah, we found some meteorites. And then we had them, and that was, in its own right, the project was a success straight off by finding one meteorite. That was like all we needed to make it a success. So we had that, and that was great. Then they built up, they found, let's call it 20 meteorites in that project in total. It wasn't a systematic search. It was basically driving around, seeing what you can find, but it wasn't doing every square meter that you can physically, that you can see.
It wasn't a grid search.
It wasn't a grid search. It was a, let's just see what the area's like. What's the crevassing like? Because that's something you don't know till you're up close and personal. You may find a lovely blue ice area, but if it's full of crevasses, you can't actually search it. And yeah, they found these. So suddenly we found two areas. One called the, oh good lord, the Witcher Nunataks. Moved down one of these down here. I was going to point generically over here. But it's around this region, and then outer recovery where the main mission was, by the recovery ice streams over here. But they were, anyway, she went to two places and found meteorites, and one of them had more meteorites than the other. That was called, we called it outer recovery, and now that's what it's called. What's the next slide? So this is from her grainy pictures. I think, why do I have the grainy? I've got the high quality ones, but I think it's because I downloaded these in Rotherham. So it was quite fun having like grainy photos sent by a satellite, even though there's high definition ones. But the point of these, this is what Katie has sent over. So Julie was a field guide. Oh no, not 20, 36. There you go. And I said that was a great. So we predicted numbers. So it's not bad in terms of the area they searched. Even though it wasn't a systematic search, you can go, well, we know how many, because we had GPS, so we knew exactly how far they had traveled, and you know roughly your line of sight, and we had predicted pretty well on that. So we're very happy. And these are the first meteorites collected. They're all that, just call it that size. And then the main product, or the main test of it happened. So we did all these testing. Oh my goodness, like I said, the logistics was just, I'm still coming to terms with it at that time. It's a very busy time. But like I said, getting things to Svalbard, getting things back, and then when you realize you've got to update something or improve something, you've got a very narrow window of engineering opportunity to do that before it's then got to go on a ship somewhere. And then you've got all sorts of customs things to go through. And Brexit had happened, and so that added things to things. But then, fortunately, we managed to get onto the one of the Bass ships to ship quite a lot down, so you then don't have to go through international customs. So that has helped things quite a lot. But going north was complicated. And then this is where to go. So this is a photo of the bases that were the field projects were being supported by the British Antarctic Survey in 1920. So this is taken in, this is on their wall in Rotherham. And so Rotherham, like I say, is up here. It's a beautiful place. Halle, the space age looking base, is over here, the one on stilts. And we were like the first aid symbol and outer recovery. So we were going for kind of a premonition for that. And the way we got there, go to Chile, down to Punta Arenas, then you've flown down to Rothera. From Rothera, we then hopped down, stopped in Fossil Bluff to refuel, then carried on to Sky Blue, a night in Sky Blue, and then from Sky Blue fly over this Berkner Island, land on this strip here, dig out some fuel from a depot there. It's literally a case of there is fuel under that snow somewhere, and you find like 100 oil drums out there. You land near it, and you'll find like basically a bit of wood sticking out. You then get a shovel, dig out the stick off the snow, bonk, you find an oil drum, get that oil drum, pour it into the plane, and then off you go again. And then eventually we got to Halle. I've got a version of this talk for nursery kids, like kids like 3, and it's great because we go over emperor penguin colonies. They don't care about the science, understandably, but I can show them videos of emperor penguins, which maybe you would prefer. So I apologise if you'd rather that. But anyway, it was wonderful. So we go over to Halle. From Halle, we then fly and made it to outer recovery. And me, Phil Guy, were the first ones out. Is this photo time of it? No, but that's the map of it. So this is outer recovery. This is where we're going. All you have to take of it is there's not that many contour lines here. They're not tightly together. So it's a relatively smooth area apart from a ridge up, these ridges up around here. But generally quite smooth. And these blue areas here are where on the satellite it comes up as blue ice. And predominantly we were at this one here, the bottom left-hand corner called outer recovery south. And that's basically that was our map. So we got our own maps printed by Bass and the cartographers put them up. So it's great. We still got these original maps of slightly strange areas. And then we got thrown out the plane, and this is what it's like. Suddenly you go from all these hypothetical things and you're building up and up and up and up and up, and then it's gradually getting more real from that bit of maths to putting it in the lab and seeing it sink, to getting a grant and then having to get the power and all the permits from the Foreign Office to say we're allowed to go here and collect meteorites, to then going to Svalbard, to the back of a Dacia Duster, to everything, to finally we can get out there looking for this stuff. And then you get deposited out of a plane. And this is, it's a digital experience. You step out and there you are. There's no kind of, acclimatization. It's like, off you go. And it's wild. And you go there and you're like, well, we know no one has ever been for this, but we knew no one's ever been there. The plane landing, loads of things broke on the planes because it was so rough. I mean, it was great fun, but it was like, oh, that was not being familiar to plane landings in the middle of Antarctica. I was like, oh, that was fun. And then the pilot was like, that was really rough. And I was like, okay. And like some of the wire cables are snapped. Anyway, so I think they were glad to get rid of us. So you're suddenly out there, and like I say, it becomes real. And remember, the temperature here was quite cold. It wasn't like none of this is stupid cold, but you talk probably about -15 sort of thing, and there's a wind chill in there. But it's not ridiculous. It's but in Halle, it was all panic there because it was so warm. It was like, -1, -2. And it was like really slushy conditions. But then you get out, and so you have one layer of clothing for that. It's basically like Scotland. Then you get here and you dress for Scotland. And you're like, oh God, it feels like Antarctica. So you quickly getting your clothes on, and you got all this, and you get your canes in to create radio, get your radio signal up, and then the plane leaves you once you're able to make established radio contact with the main base. So the first bit is to do that. Field guide, his first ever time being a field guide. Got on really well with him, but he was just like, I definitely know what I'm doing. And so it was really good fun. But it was wild, that first bit. And this is the tent. So this is us, and goodness knows what time it is, call it midnight. But it's basically like this the whole time. It is magnificent. If you're into your clouds, yes, go to Antarctica. So you get a whole different climate there. So you get different clouds. And it's fantastic. I think this would have been at night because the sun's quite low. And these two things here are radio. So the two canes up here. And at this time, it was lovely. It was just Rob, myself, and then they managed to fly Valter out. So 3 of us. We had, what I really enjoyed, there was no generators. We didn't have any batteries at this time. I was waiting for the rest of the equipment to come out. So it was really actually enjoyable, just completely, literally off grid and just self-sufficient. It was so much fun. And you just got your pace. It's someone who's naturally always on, as it were. It was nice to have no option but to be like, you know what, I'm going to lie in for 50 hours or something. And it worked really, it was very enjoyable, very beautiful. And this is the 3 of us in the tent. You have these tents, what they call, I'm going to call it a Scott tent, but maybe it's a Shackleton tent. I'm pretty sure it's a Scott tent. Anyway, it's basically a triangular prism, and you can fit 3 in a tent. You have a cooking thing in the middle. It's slightly uncomfortable, but it's not too bad. Yeah, you'd be happy. And you just got all your stuff, and then like I say, you just find your own kind of thing. It's like, yeah, it's amazing how humans, you just adapt quickly to your conditions. But yeah, so this is Rob, he's the field guide. Wouter, he's a brilliant engineer with us, and that's myself. Yeah, in there. And then this was the other tent we had out there with us, was for the start of the project, it's the toilet tent. So how it works out there, you basically dig a hole in the snow, have a very small tent on top, and then you basically go down some steps into the toilet. So it's actually quite sheltered. So you've got these two tents. You already have to see one picture like over there. I got that because I think I'm taking the photo from the toilet tent, looking back out. And part of the fun, and this again, we had this out there, was this stuff. And we knew, so you have your food's basically freeze-dried stuff. You could have other things as well, but you have a lot of freeze-dried food. It's actually really nice. Apart from this, so the freeze-dried pasta lasagna, and we were told some of the freeze-dried food is contaminated. And so you go out and you're like, all right, okay. And you don't know. And so you're rolling, you don't know what's going to happen. And then suddenly you get the shits. And a few of you get the shits. And you're stuck in really cold conditions, crawling distance from a toilet tent that you need to go down in the freezer. And it's horrific. And so between all of us, we all got ill. We're like, but it's not all the time. It's like you're literally rolling the dice. You don't know which one of these is contaminated. Awful. And be kind of fun if you're in a student house or whatever. But here you're like, it's so cold. And it's, yeah. So that was added a kind of amusement to things, to say the least. And it was, yeah, it was quite shocking. It's like, why can't you guys get some new food or something? I mean, when does it even say when it goes off? Yeah, best before 2017. Thank you. Yeah, exactly. So they gave us that. And some of the stuff went off for years before that. But freeze dry is great. If you're ever into your prepping, get loads of it because it lasts for decades, apart from this one. Exactly, army rations would have been good. Anyway, yeah, so that added a bit of fun. And whilst we were waiting there, here's actually some blue ice. So here's us looking for some meteorites and some nearby blue ice. We didn't have the skidoos yet, but we've got to midnight. It's like, you know what, should we go and have a look?
Cirrus there on the left there with the halo, the colour of the there. And just at the left of the sunset.
Cool. So I would love to say we saw stars and things, didn't see a single thing. But that was basically, yeah, we got all these high clouds and it was just magnificent. So again, we went out walking at night. So we kind of like, well, you piece out routes where there's no crevasses and you kind of put it together. And when you're on this, you can see crevasses easily. So when you're on the snow, you can't. So we were able to go ahead and just go out looking at night because we were getting a bit bored waiting for the other planes to come out. So it was like 10 days we were there, just there, going to the toilet tent and back. And so it was, yeah, so we were able to go out and just finally look for meteorites. Didn't find any at this moment. And then we finally got the skidoos and we were able to go to the main base. We made our way round. And then after all of those years and messing around and getting things wrong, we were just driving along. We didn't have the equipment yet. We didn't have the metal detector equipment, but we had ourselves. And we were like, right, let's go and find some meteorites. And myself, this is me here, Rob took the photo, Rob and myself were driving along. And suddenly, I remember Rob like pointed and I looked up and was like, oh my goodness. And it's just like, suddenly, there's a meteorite. You've got all those years, this hypothetical idea. And I said, it gets increasingly real, but you can't quite believe you're just going to find a meteorite where you predict it. And then suddenly it was there. And that's a really big guy. It's like this big. So it's an absolute whopper lying on the surface. And there's obviously a bias there. When you go somewhere for the first time, you see the bigger ones first. Okay, because they're the first ones you see. You don't care about the details. You don't see the details. So you find these huge things, and it was surreal. It was like, wow, that's like life goal or life objective complete. As you can see, it's a bit cold, so we're all wrapped up in here, and gradually we get more and more layers on as the weeks went on. And then basically the first thing you do is just a lot of posing. So you're just sitting around like, here's me with meteorite and stuff. And yeah, there's a lot of that. This is not an impact crater, I would add. It's just because it's probably melted in, it's warmed up the ice around, but it's helped sublimate it to warm it up. So you get, so hence, yeah, adds a bit of legs to the theory. But yeah, that's Rob posing there. And then this is when Katie and Roma came out to join us, the meteoritists came to join us. We were then able to get away from the landing strip we built, drive in convoy with all our equipment to be next to the blue ice. This is the blue ice area here, so we're camping right next to it. You don't want to really be camping on the solid ice. Even though it's secure in many ways, because you can see crevasses, it's a bit uncomfortable. It's hard to get pegs in and basically get a tent secure in solid ice. But this is the camp here. So we got 1, 2, 3 tents and a toilet tent. So I think that's a skidoo, but I think that's the toilet tent there. So And that was our base. I think by then we're probably the furthest people south from the UK. I've got the damn lats. I think like it's not on my bag. That's Rotherham. So I am going to go back. Was it 70? Hang on, I'm going to go back for my own. We didn't even show on there. Ah, I'm going to call it 80 degrees south. It wasn't. It was south, but it wasn't stupid south. There we go onto that. But it's about of the order of 80. It wasn't 85 plus. And yeah, and then the equipment. So this is us then towing along, having a look. And what we had was the equipment testing, and it would start to break pretty badly out there. So it worked because we set up again to test it again. We had everything in the protocol of like, well, we'll take the equipment, we'll set up a runway, a strip where we can drive up and down the equipment. We put meteorites or decoy meteorites in, and bing, you can pick these things up. So we know it works. So you're happy with that. The trouble is we'd also put in accelerometers into the equipment. And we've done that in all the other places we've been to. We've been to Svalbard, where it was on ice, but with a nice snow covering, so it's quite smooth. We've done it in the field, vaguely smooth. But we'd also done it in Sky Blue, a blue icy area in Antarctica the year before. And we got nothing like the impacts this was getting. The ice was much more scalloped than we had been before. And so the system, we're getting 10 Gs being put through the system multiple times a second. So any loose nut, bolt, wiring, yes, just bang, 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 the whole time. Because all these scallops are about that long. So you're driving along, each one is just smashing it to bits. So any weakness is exploited straight away. And that you then get like a propagating fracture, essentially, when something's broken inside a box. Fine, we're going to fix it. You have to lift the box open. What you never want to do is lift the box open. It's like saying you got a problem with a laptop. Do you mind going out in the pouring rain, just unscrewing the keypad and just finding the issue? And it's like that. You have to go, oh, let's get this out. And then you're covering it from spin drift and so forth, getting something out. That can introduce problems. And also you've broken, a lot of times you
do this.
exactly. And the nut goes, you're into the snow. Okay, so it's something like, oh, you've then got to find that. So your gloves are off, your hands are cold. Well, that's exactly what we did. Amusingly, it did work. So a couple of times it did ping, and we found spanners that we lost. So I was like, but the trouble was the ratio of time fixing to using it went down and down, or went up and up and up. So we're spending more and more time fixing as opposed to looking for stuff below. And it starts off like this. So you can see exactly, I mean, like I say, it worked out there. It was getting properly impacted. And when we did have occasionally a dusting of snow, it's actually quite easy to search because you can see the tracks of where you've been. So you just follow up, and we had obviously what GPS systems we were following. So you're going up and down these transects, looking for the meteorites below. And then yes, that's all fixing problems in there. But yeah, you can probably see the scallops quite clearly over here. And we had a huge, great bash on the front to bash through the snow. But yeah, I mean, we could have dropped the speed quite a bit, but again, that signal processing we had tuned to be like 10 kilometers an hour. So we could have made it slower, but then you got to adjust in real time the signal processing, which we could do and did. It all just adds time. And then by the end of this midway, so you can see down to 3 pounds, we had 2 of these systems, and they're all doing the same. So it's a bit like, you know, a child losing their teeth. And then you start with lovely, beautiful baby teeth, and then you become like a ghastly something or other. So we're down to 3 by here. And we're driving along, you're still finding things, but then you kind of all do, what happens if a meteorite goes in the middle? Oh, that would have been annoying. Would have been really annoying. But yeah, so you're carrying like this, and then you're getting colder and colder and colder. And obviously, as we're going along, though, we're collecting meteorites on the surface. And the vast majority of meteorites are on the surface. They always would be. If the theory was correct, 95% are on the top. Okay, so we were doing a lot of collecting of meteorites, but just not below the surface. And so on the top, here's a good example. So you find one. And this is one of our ones out there. This is when we did a little foray somewhere else to another ice field a bit further up when we drove for it, did a day trip. We got to name this mountain. It's called Mount Halliday. It was the person who came up with that curve I showed before from Canada. And you find one, you can see it's pretty small. And you get your tongs out. You basically do lots of photos of it. You write stuff in your notebook, have some tongs, put them into a plastic bag, basically, but a decontaminated, whatever it's called, plastic bag. So you write stuff on that. That then gets put into a pouch, which then gets put into frozen storage. And then you can see it. for like a year. Because then it's in frozen, then it goes to the base and gets flown back, or taken back by ship.
You can see the scalloping of the surface.
Yeah, exactly. You see it, so this is like a centimeter here, so you can see all of this impact going on. But yeah, it gives you an idea of your collections there. Christmas Day, this is us. So we got a cake given us by base, so it's great. So Merry Christmas, you filthy animals. So those of you who's watched Home Alone. So yeah, Christmas Day was lovely. It was quite fun because by then we kind of knew what was happening with the equipment. But it was also quite amusing day. And we went up to one of the ridges behind us. And there's like this ice rise really high, about probably 100 meters up from where we were a few kilometers away. We went up, so the base was down over here. And then we came up, this rise suddenly came up. And this is the summit, this kind of strange protrusion up here. But yeah, that's us on Christmas Day at the high point in the whole area, somewhere in the middle of Antarctica. And how's that for a sunset? So it was cracking. So there's lots of highlights to it. Yeah, that's a great view from it. Then you've got the recovery glacier. The recovery, I hope I don't make up the story. The recovery is because when Hillary and whoever were crossing Antarctica, they lost loads of equipment in an ice stream. And they were like, oh, whatever, fed up, just leave it there. They then realized they actually needed it. They had to go back to the ice stream and recover the equipment from there. So again, you got this story of the recovery, and that's why we called it outer recovery, just because on my notepads in the office, I was like, well, it's outside the recovery ice stream, it's outer recovery. And then suddenly it got officially named outer recovery. But yeah, that's just at the top of it there. And yeah, then we obviously there's a lot of posing. This is what we named Mount Halliday. So we walked up here. That was really nice. That was like our day out was a drive up here. We found that without the equipment on the back. And then walk up here up to the top. Do I have a photo up there? Yes, that's us on the summit of it. So you can see we're all looking a bit, my beard's getting bigger and stuff. Everyone's looking a bit colder, but it was great. It was, but yeah, I'm really interesting. We collected lots of rock samples from here as well, which will come back. And we did outreach stuff. So part of it, there's like lots of schools had sent things out to say, can you take photos of certain things like whatever, I love snow. So exactly, yeah, so you do lots of things where you then pose in front of a meteorite. Or something, and then you do a satellite upload of the data. Oh, we must have sent it back by satellite somewhere. But yeah, then there's us on the top here, basically just a lot of posing. But as you can see, it's getting, as the time went on, you kind of get used to it, but also as the fatigue gets in, you get colder and colder as well. Yeah, go for it. Oh, we operated on, that's a great question. Can you remember? I think UK time. You should choose what you want. Yeah. So we were on. We each basically on different ones. I think we're on just UK time. And the reason why is because you'll want to be in communication with Cambridge, UK, where's where BAS is based. So you want to, because on the bases, the phone connection is really good. So if something's happening or you need to get information, someone's still in the office. So you want to be on the same time zones. So basically on Cambridge time. So yeah.
You could choose.
So yeah, you can do because there's all choose what you want. But yeah, it's most convenient to be on that time. What is that? Yeah. Trying to remember probably just through stress. I think it was the did we lose it? I don't. Yeah. I mean, it was cold, but it wasn't brutally cold. It was I mean, it started being Scottish winter for the time, so not ridiculous. No one was dying, but you're just cold. And yeah, I mean, we just also eat loads of chocolate and junk and peanut butter and stuff. So we didn't come out morbidly obese. We didn't come back skeletal either. I would say. So yeah, it was on our minds. I'll be losing weight, gaining, but it was like, I don't know. It was also you're doing lots of physical lifting and things as well. So we were working, but when you're sat on your backside in the skidoo, you're not really doing much either. But yeah, we didn't come back too bad, I think. I'm almost at the end. Right. That's our last meteorite. That's the end of the metal detector equipment. So we got down to one. And so we're one panel by the end, and that was the final meteorite found. But yeah, so you can see what we were down to by then. It was just literally one out of the two systems we had. That was the one. But yeah, you can see the scallops in there. So that was it was slightly bittersweet, but at the same time, we found a lot of meteorites. And the what's the punchline here? So we found 121 meteorites. 75 have been named officially so far. The rest are getting imminently about to be named. So it goes to some international committee of meteorite, something or other. It's not my expertise. I find it a little bit someone else's problem. So, but you kind of bring the meteorites back. But we collect 121 meteorites. So super happy. So when we went to the start of the project, having nothing and no idea, we suddenly brought back a good haul of meteorites, and that's a decent number. And we'd systematically, looking on top of the ice, collected pretty much all there was to collect. And it was bang on what we predicted from that other model. So that model before can now be used by other people to work out, not anyone else internationally, to work out how many meteorites they expect to collect from certain areas in Antarctica. So it would really help improve that. It just shows that consistency with everything. So I'm over the moon about that. For me, that was the best result. In terms of proportions, did we actually find any ions or stony? We found 2 stony ions on the ice. So that gives, of that 75, 2.7% iron or stony iron. And this, bear in mind, it was 0.7 versus, we'll call it 6%. So basically in the middle. So what we ended up with is a null hypothesis. So the hypothesis very much still stands, that there is a lost layer of meteorites, but our searching for it was inconclusive. We didn't search enough. We searched 0.75 square kilometers. Yes.
Could ground penetrating radar be used?
Yes, it could. It was even more experimental technology and far more expensive. Because I think the actual cone it can see through is quite narrow. I'm not an expert in GPR, but most of the time we went through it and they go, well, when you basically do it back of the envelope, well, it's great if you're searching that much, but I need to be searching, a huge area each day. And it was a mixture of what actually cone can it see combined with the cost. And the budget of this, I think, had £200,000 for the entire, which may sound a lot, in many ways, it's a huge amount of money. It's absolutely peanuts when you've got to employ a load of people and get this going for 3 years. And every single bit of that equipment is basically just a lot of thieving and begging from all sorts went on. And yeah, so I would have loved to give that a go, but that is still definitely a possibility. But the other thing is we now know how to fix some of the equipment. I think we just pour resin into the electronics all the time just to make it so nothing can vibrate. But yeah, we kind of got that slightly amusing result. But like I say, we found, it was 121 meteorites. They're now in the permanent collection of the Natural History Museum down in London. So as part of this, another part of the film was to actually go down to the vaults of the Natural History Museum and like, oh, there's the results of the Endurance expedition and all sorts of amazing natural history. Like, oh, there's our work there. So it's all quite amusing. But yeah, they're still there. It doesn't junk the theory. The theory may not be true. If physically it's possible, because you do find stones sunk in to the ice, and in one of those regions, all the stones from that mountain had sunk in to the ice. So physically it works. We know that. But does it for definite explain that the iron meteorites being the thermal conductivity being the cause for this? We can't say for definite. So that was frustrating. But we got so many other results out of it that, to be honest, that was probably future science-wise, that was probably the least important thing. Popular science-wise, definitely the most important thing. But yeah, it was kind of a bit of a blast. And there was a lot involved in the whole thing. Yeah, like I say, I didn't even go on about, I could have done a whole talk about chainsawing in Antarctica. But anyway, that was the whole thing. But anyway, I'll leave you with that. But hopefully that makes vague sense. It's kind of a whistle-stop tour of a lot of confusion for those years. But it was great fun. Cool. Thank you very much. Okay.